Welcome. In this video we start Unit 12 on logarithmic functions. Day 1 is just about logarithmic functions in general. What are they? And from the book we're looking at section 6.4. We'll cover objectives 1, 2, and 5 today. Here we go. Exponential and logarithmic statements. So the big idea, I just cannot emphasize this enough, is that logarithmic functions are the inverses of exponential functions. So whenever I need to work with logarithmic functions, very often I turn it into an exponential expression, and then that's easier to solve. Here's some examples. Log base 2 of x. That's a function, and that function is the inverse of the 2 to the x function. So here's a quick example. In the exponential function 2 to the x, let's suppose I put in 3. So that looks like 2 to the 3. And then the output of that is 8. So I put in 3 and I get out 8. Well, the log base 2 function takes the 8 and gives back the 3. They are inverse functions, the exponential function 2 to the x and the logarithmic function log base 2 of x. Log base 10 of x, that's the inverse of the exponential function 10 to the x. Log base 1.05x, that's the inverse of 1.05 to the x. And then this last one is interesting. We read this as the natural log, and that's the inverse of e to the x. Actually, you could write this as log base e of x like that, but we often just write ln x for short, ln as the natural log. Let's see some examples of how these statements convert back and forth. So remember, for example, log base 2 of x is the inverse of 2 to the x. So if I have an expression like 2 to the 5 equals 32, I could rewrite that as a logarithmic expression. Log base 2 of 32 equals 5. So I always think with the exponential function, there's the input is 5, and the output is 32. And then the in and the out, they get reversed. For the logarithmic function, the 32 is the input, and the output of the function is 5. So let's think about that when we try the next three. 3 to the 4 equals 81. So I have an exponential function that took 4 in and produced 81. So I can reverse that, and I can say, look, here's a logarithmic function, log base 3, and I put in 81, and I'll get out 4. How about the next one here? 10 to the 4th equals 1,000. Here's my exponential function, and I put in 4, and I get out 1,000. So the inverse function will be log base 10, because remember, whatever the base of the exponential function is, that's the base of my log. And now the input is 1,000, and the output of this function is 4. Last example, it has some fractions. That's okay, we can use fractions with logs also. My exponential function is 2/5 to the 3rd, and so 3 is the input, and 8 over 125 is the output. So what is my log function? It's going to be log base 2/5. That's okay to have a base of, that's a fraction. Log base 2/5 of, I'm going to take the output from the other expression, so 8 over 125, and the answer to that is the input to the original function, so 3. There we go. Let's go in the other direction. Let's start off with a logarithmic expression and turn it into an exponential expression. Log base 2 of 32 equals 5. So the corresponding exponential is going to be 2 to the x. It's that function. But in the log, 32 was the input, 5 was the output, so those get switched. So my input is now 5, and the output is 32. That's the way of reversing it around. In the next example, my log base 10 of 10,000 equals 4. So my exponential function looks like 10 to the x, so 10. And what's the input now? It'll be 4. And the output is 10,000. If you just want to remember, when you're presented with a logarithmic function, remember the base of the log becomes the base of the exponential function, and whatever your solution is, that becomes the new exponent. So in this next example, I see the 6, I'll put the 6 right there, the 2.57, 2.57, that's my new exponent, and the solution to that is the 100. And this is just an approximation, so we'll keep it approximation. And the last one, how about this? The corresponding exponential function looks like 4 to the x, so 4 to the something. What am I plugging in? Oh, negative 3. 4 to the negative 3 equals, and then 1/64th. Does that look right? Does that seem reasonable? Just to double check real quick, 4 to the negative 3 is the same thing as 1 over 4 cubed. Oh yeah, and now 4 cubed, that's just 64, so that looks good. Let's do some corresponding statements with e and natural log. So e to the 5 is approximately 148.413. What does that look like as a natural log expression? I need to take the natural log, and now previously 5 was the input, 148.413 was the output, so now those get reversed. 148.413, that's my input, and my output will be 5. And I guess my original expression was an approximation, so I'll make this an approximation also. How about this next one? Natural log, and what goes in is the x, and what comes out is the 7. If I start with the natural log, well, the inverse of natural log is e to the x, so I'm thinking e to the x, e to the something. What goes in here? Well, in my original expression, x was the input, 16 was the output, so now I get e to the 16 as my 16 becomes my input, and x becomes my output. And last one, again, I have natural log of 5.3 equals x, so I have a natural log function there, so the inverse function for natural log is e to the something. And what goes in? Let's see, previously 5.3 was the input, x was the output, so now x becomes the input here, and I get 5.3 as the output. There we go. Let's evaluate some of these logarithmic expressions. Instead of just converting back and forth, suppose I have the log base 2 of 16. I mean, what is that number? What does that become? So the way to do this is to write, kind of make a little equation to solve. Log base 2 of 16 equals x. So now my goal is really just to figure out what is x. And now, here's the key idea. Convert it into an exponential equation. So this becomes 2 to the x equals 16. And now this is easier to solve. So with your calculator, or just with some little calculations, you might be able to realize, oh, if I take 2 and raise it to the 4th power, I get 16. So the answer is 4. For some of these beginning problems, the answers will be obvious enough that you can kind of work them out with a little bit of intuition. In this second example, log base 3 of 1. So let's say log base 3 of 1 equals x. So log base 3, what's the inverse function? That's 3 to the x. So this becomes 3 to the something. Oh yeah, 3 to the x equals 1. 3 to the something equals 1. What is that something? Oh yeah, that has to be 0. So my answer is 0 there. So the answer to log base 3 of 1, that answer is 0. And last example here. How about this? I'll write log base 5 of 1 over 125, that equals x. Let's convert it into an exponential statement. So that becomes 5 to the x equals 1 over 125. And now we're sort of back to a previous lesson where I had to solve some exponential equations. I need to find a similar base. That's really what I need to do. So let's take this 1 over 125. That's the same thing as 1 over 5 cubed. And now I can write this as 5 to the negative 3. So here we go. I've got 5 to the x equals 5 to the negative 3. So that tells me x equals negative 3. And let's evaluate some logarithmic expressions where e is involved. So how about this first one? The natural log of just simply e. So let's say the natural log of e equals x. Remember, natural log, that's the same thing as log base e. So I can think of this as e to the x equals e. Oh, well, e is just e to the 1, so I have my solution x equals 1. So there we go, natural log of e equals 1. How about let's compute the natural log of 1. All right, so natural log of 1 equals x. This tells me that e to the x equals 1. And oh, here's another case where my exponent has to be 0. So x equals 0. How about this next example on the top right? Compute the natural log of e to the 4. Natural log of e to the 4 equals x. So e to the x equals e to the 4, and so x equals 4. This problem sets up a nice general statement for us that we can use often. In fact, the natural log of e to the anything, natural log of e, I don't know, to the anything, right? That answer to that is going to be that anything again. So, and this is because natural log and e, these are inverse functions. Whatever e does to the star, the natural log will undo that. So, the natural log of e to the 17 is 17. The natural log of e to the 4.09 equals 4.09. The natural log of e to the 13x minus 1 equals 13x minus 1. This is a handy observation to remember. Last one, let's compute the natural log of the cube root of e. Seems a little bit weird and tricky, right? Let's remember that the cube root of something is the same thing as raising it to the 1/3 power. So that's the same thing as trying to figure out the natural log of e to the 1/3. Oh, and look at this, what I discovered up in my previous statement. Remember, the natural log of e to the anything is that thing again, so I simply get 1/3 as my answer. All right, let's solve some logarithmic equations. Let's solve log base 4 of x equals 3. How we always do it is the repeating theme again and again. Let's convert our logarithmic statement into an exponential statement. This statement involves log base 4, so the exponential function that I'm going to use is 4 to the x. Let's see, so 4 to the something. Now, in my original statement, x was the input and 3 was the output. So now 3 will be the input and x will be the output. And I have this equation, 4 cubed equals x. Oh, and I think I can solve 4 cubed. I mean, that's 4 cubed looks like 64. So x equals 64. And there's the solution to the problem. How about this next example? Same idea. Now my exponential function is 2 to the x, so 2 to the 10. 10 is now my input, and my output is 2x plus 20. Well, 2 to the 10, that ends up being 1,024. So 1,024 equals 2x plus 20. I'll subtract 20 from both sides. So 1,004 equals 2x. And I think if I divide both sides by 2, I'll end up with x equals 502. There we go. What if the variable in my logarithmic equation happens to be in the base? Well, these aren't really any more difficult. In fact, maybe they're even a little bit simpler. Let's see here. This converts into x squared equals 64. Do you know the square root of 64? X equals 8. And how about log base x of 8 equals 3? So I get x cubed equals 8. And what number cubed equals 8? How about 2? X equals 2. Now, one last quick note before we leave this slide. You might be wondering, back in this previous problem, since x squared equals 64, couldn't I also have negative 8? Is that an additional solution? And the answer is no, it's not. It turns out that, recall that for the base of an exponential function, I can only have positive numbers in there. And so similarly, for the base of a logarithmic function, I can only have positive numbers. So it has to be the case that x is strictly greater than 0. And so since I know that x is strictly greater than 0, then when I solve the equation x squared equals 64, I only care about the positive solution. All right, last idea. Let's solve some logarithmic equations that involve e and the natural log. How about this one? Solve e to the 2x minus 1 equals 5. And here's a new instruction for us. Express the answer in terms of the natural log. Well, let's see what happens. The inverse function of e to the x, the inverse function of that exponential function, is the natural log. So I have the natural log. And previously, in my original expression, 2x minus 1 was the input, and 5 is the output. So now this becomes the natural log of 5. 5 becomes the input, and 2x minus 1, that's the output. So I don't really know what natural log of 5 is. Well, I mean, you can plug it into your calculator and get an approximation. But in terms of an exact answer, natural log of 5 is the best you can do. So just leave it, the natural log of 5, and let's do some arithmetic with it. So I can add 1 to both sides, and I get the natural log of 5 plus 1 equals 2x. And then I can divide both sides by 2, and when I do that, I end up with x equals natural log of 5 plus 1 all over 2. And there we go. There's my solution. That's solving for x. And I've left the natural log of 5 just in there as the natural log of 5. And that's what it means to express the answer in terms of the natural log. Last one. Solve the natural log of e to the 7x equals 35. Well, this one looks more complicated than it really is. Natural log and e are inverse functions, so when you see them nested this way, we know that this left-hand side boils down only to 7x. Remember, the natural log of e to the anything is that thing again. So the natural log of e to the 7x is 7x, and that equals 35. So my answer, divide both sides by 7, is 5. There we go. This has been our introduction to logarithmic functions, and the big idea just keeps on coming up again and again and again, is that logarithmic functions are just inverses of exponential functions. We aren't as familiar with log functions as we are with exponentials. They just don't seem as natural to us. So whenever you're presented with a logarithmic equation to solve, the key idea is transform it into an exponential equation, and then it becomes a little bit easier to handle. All right, and this is a good place to stop.